Ever wonder how the digital infrastructure behind massive global platforms holds up under literally millions of users logging on at the exact same second? Well, let's dive right into this explainer. We're going to see how software engineers keep our favorite apps from just completely crashing under that intense pressure. And spoiler alert, it all comes down to mastering algorithm complexity.
Before we even touch the formal math, we gotta ask, how do developers know for sure their servers will survive a massive traffic event? Think about the insanely anticipated Diablo 4 beta launch, right? Under normal workloads, everything runs smooth as silk, but during peak events, systems get pushed to their absolute limits. If an essential service relies on a poorly scaled algorithm, a sudden spike in users can cause total memory exhaustion, just cascading failures across the board. The secret to preventing that nightmare? It lies in a concept called asymptotic complexity.
So we're going to break this whole thing down. We'll start with the language of efficiency, meet our main players, O, omega, and theta, look at cases versus bounds, calculate some algorithm complexity, and finally see how this all scales in the real world.
All right, part one, the language of efficiency. This is the math behind the code.
You know, it's actually fascinating how these notations evolved from pure number theory into the ultimate toolkit for computer scientists. Back in 1894, a mathematician named Paul Bachmann introduced big O notation just to capture function growth bounds. Later, in 1914, Hardy and Littlewood brought in big omega. But here's the kicker. They used these strictly for pure math. Early computer scientists actually struggled to use them for software. People were misusing the terms left and right, assuming big O just meant an algorithm was inherently slow. It wasn't until 1976 that the legendary Donald Knuth published a seminal paper. He formalized these concepts specifically for computer science, giving us the strict definitions that engineers use today.
Moving right along to part two. Let's meet O, omega, and theta, the three main bounds of our explainer.
First up, we have big O. You can think of big O as the absolute ceiling. It cautions engineers about the maximum amount of time or memory an algorithm could possibly consume as inputs grow. Basically, it's the ultimate mathematical boundary for the worst-case scenario. It gives you a rock-solid guarantee that your algorithm's resource consumption will never exceed this defined curve, even as your data approaches infinity.
Conversely, we've got big omega. If big O is the ceiling, big omega is the floor. It defines the lower bound, the absolute best-case minimum resources an algorithm is going to require. It basically tells developers, hey, no matter what happens, this code will never run faster or use less memory than this specific baseline. It's super helpful for identifying situations where an algorithm is hitting its absolute optimal performance.
And finally, we have big theta. Big theta is kind of the Goldilocks zone. It's the just right sweet spot. It captures the range where an algorithm's efficiency is asymptotically tight from both above and below. So when big theta exists, it gives you a highly precise understanding of behavior across different inputs. Why? Because the upper big O limit and the lower big omega limit are actually growing at the exact same rate. Look closely at how this plays out visually. That dark red line, that's your upper bound, big O. The green line is your lower bound, big omega. And because those two lines are growing parallel to each other at the exact same rate, the actual function, which is that wavy red line in the middle, is perfectly sandwiched right between them. This means big theta exists, and that gives us a really predictable order of growth. But, as we all know, things aren't always so neat. What happens if the bounds drift apart? Like in this scenario, where the dark red upper bound is increasing linearly, but the green lower bound just stays perfectly flat and constant. When that happens, a single big theta bound simply cannot exist. There's literally no single function that can describe both the ceiling and the floor because, well, they're behaving entirely differently.
All right, section 3, cases versus bounds. Time to bust a very common big O myth. So, a lot of people mistakenly believe that big O simply means worst case, that big omega means best case, and big theta means average case. But actually, scratch that. Case analysis and asymptotic bounding operate on completely different logical levels. A case describes a specific scenario, like say whether the item you're searching for is the very first item in a list or if it's completely missing from the dataset. A bound, on the other hand, provides the mathematical limits for that specific scenario. Take a binary search tree, for instance. Even a worst-case scenario mathematically has its own distinct big O, big omega, and big theta bounds. Let's look at the worst case, where the value isn't even in the tree, and the tree has devolved into just a linear list shape. The big O upper bound is O of n, but the big omega lower bound for that exact same worst-case scenario is also omega of n. You see? You can mathematically define upper, lower, and tight bounds for literally any case.
Moving to Section 4, Calculating Algorithm Complexity. Let's turn some code into math.
So how do engineers actually calculate these limits in the real world? They use a surprisingly simple four-step process of algebraic simplification. Step 1. You count the basic primitive operations, things like arithmetic, assignments, or comparisons. Step 2. Express that count in terms of the input size, which we call n. Step 3. Keep only the highest order term. Why? Because as data grows infinitely large, those lower order terms become totally negligible. And finally, Step 4. Drop the constant multipliers. By following these exact steps, engineers can simplify some really messy equations. For example, an equation of 2n plus 2 operations, that gets mathematically reduced down to a clean, simple O of n.
Now this chart right here is the ultimate cheat sheet. It visually represents how different algorithmic growth ranges scale from absolutely excellent to, well, mathematically horrible. That green zone? Those are highly efficient algorithms that stay blazing fast no matter how much data you throw at them. But as you move up into the yellow, the orange, and finally that scary red zone, the number of operations just skyrockets aggressively as the elements increase. If your algorithm lands in that red zone, your system is in serious danger of crashing under heavy load.
Here we can see the formal hierarchy of dominance, going all the way from O1, constant time, down to the dreaded On factorial time. This perfectly illustrates how quickly algorithms can become completely intractable. Let's zero in on O to the n, exponential time. That's where the runtime literally doubles with each single addition to the input. To put that into perspective, think of the classic chessboard problem, where you double a single grain of wheat on each square. By the time you hit the 64th tile, you'd need roughly 9.22 quintillion grains. That is about 184 billion tons of wheat. No way you're processing that. And that is exactly why exponential growth rates quickly become totally impractical for large inputs.
All right, our final section, number 5, scaling in the real world. Let's talk about why precision really matters here.
Think of algorithmic efficiency kind of like delivering pizzas. If you have high spatial dispersion, meaning you have to deliver to n different guests at n totally unique distant locations, your total travel time scales quadratic. That is your worst-case O of n squared scenario. But what if you consolidate the workload? What if all n guests gather at a single party? Suddenly, your travel time remains constant to that one location, effectively collapsing the complexity to a linear bound of theta n. In software engineering, this is the exact difference between fragmented memory access and cache-localized processing. Consolidating your memory access is just like delivering to one massive party. It vastly improves performance, even if the underlying task seems practically the same.
And this is exactly why engineers constantly hunt for tight bounds, rather than just settling for loose ones. In mathematics, if an algorithm runs in linear time, yeah, it is technically correct to say it's bounded by an exponential upper limit. It fits the definition. But, as the quote goes, stating you have at most $1 million when you actually just have $10 in your pocket is technically true, but it severely lacks precision. A loose big O bound might be mathematically accurate, but it is totally useless for predicting actual server load. Engineers absolutely need that precision to allocate server resources correctly. Ultimately, knowing your bounds gives you the superpower of prediction. It completely removes the guesswork from software engineering and replaces it with cold, hard, mathematical certainty. Whether you're dealing with a tiny local app or a massive global server launch, asymptotic complexity is the tool that ensures your system stays stable. So I want to leave you with this final thought to ponder. If your code encounters a massive traffic spike tomorrow, are you just crossing your fingers and relying on the best case, or are you mathematically prepared for the worst?